All right. In chapter 3 is called linear systems. We're going to be going through sections 1 and 2. Section 1 is solving systems using tables and graphs. Section 2 is solving them algebraically. So in this particular section, we are strictly focused on linear functions. Up to now, you already know or should already know how to solve equations. But now we're going to practice solving more than one equation at the same time instead of one equation at a time. So we'll start with this first definition. So a linear system of equations. A linear system of equations is a set of two or more equations using the same variables. And I'm just going to go ahead and put it aside, just put the word linear, because can you have a system of quadratic equations or cubic equation or a system of polynomial equations? Yeah, of course you can. Of course you can. But here we're strictly going to focus on linear equations. Okay, and that's two variables, x and y. Eventually we'll upgrade that to solving systems of equations in 3 variables, but at the very most, you won't have any exponent higher than 1. So the solution of a system of equations, what does a solution look like? Well, a solution of a system of equations is the set of all ordered pairs that make all the equations in the system true. So if I'm solving a system of equations and I find my solution, it's an x and a y value, or if you're doing 3 variables, an x, y, and a z value that fit in all of the equations in that system. Now, if we're talking about how to solve it graphically, which is what we're going to focus on in this section, graphically the solution can be found on the point where all the equations in the system intersect. So in section 1, that's the focus, is using a graph to find the point where all those lines intersect. And that's where we have the solution for a system of equations. Okay, let's look at an example. So here's a system of equations. I have negative 3x plus 2y equals 8, and x plus 2y equals negative 8. So by graphing these, so this is in standard form, obviously you can convert that to slope-intercept form and graph the points using the slope and the y-intercept. And this is what their graphs look like. If I zoom in here, this right here is the point where they intersect. This is the point negative 4, 2. Now, if I look at these two equations right here, if I plug negative 4 and negative 2 into the x and y values respectively, what's going to happen is negative 4 here and negative 2 here make this entire expression equal to 8. In the same way, plugging negative 4 and negative 2 into this equation, or into this expression, will make the value of that equal to negative 8. Watch, I'll write it down. I'm going to write it down so you can see it a little bit better. So, for example, if negative 4 is up here and negative 2 is up here, right? Negative 3 times negative 4 is positive 12. 2 times negative 2 is negative 4. Add that together and I get 8. If I do the same thing down here, so this x is negative 4. 2 times negative 2, so that's plus negative 4 here. Negative 4 plus negative 4 equals negative 8. So whatever solution that you come up with should be the point where they intersect. And so whatever your x and y values are, they should equal to the other side of each equation. Okay? You could also use, again, putting it in slope-intercept form, you can also use a graphing calculator to do it. So by putting them in slope-intercept form using these two equations, if you go to the x and y chart on your graphing calculator, just look for the place where they have the same y values, right? So for example, down here when x is 0, I have 4 and negative 4. It's close, but it's no cigar. But if I look at negative 4, again, they both share a y value of negative 2, okay? So let's apply that logic to this example. X minus 2y equals 4. 3x plus y equals 5. How do I solve this? Well, the first thing that I want to do is I want to write both of these equations in slope-intercept form. That way I can put them in a graphing calculator or a graphing tool and find where they intersect. So here, I'm going to subtract x on both sides. Oops, sorry. Did the wrong thing there. So I'm going to subtract x on both sides. So that's negative 2y equals negative x minus 4. I'm going to divide both sides by negative 2. So my slope-intercept form for this first equation is going to be y equals negative 1/2 x. I'm sorry, that should be a plus, my bad. Let me erase that negative sign here. So again, because negative divided by negative is a positive. So 1/2 x plus 4. And then I'm going to do the same thing here, but here I only need to do one step because I only have a y here. So I'm going to subtract 3x on both sides. My other equation is going to be y equals negative 3x plus 5. Okay, those are the two equations that I'm going to use to find the graph of these functions. So for both of these graphs right here, my y-intercept is 4 for one and 5 for the other. So I'm going to switch over. Let's see. I'm going to switch over to Desmos real quick. Okay. So you guys can kind of see what I'm working with here. So here's 4. Here's 5. Those are the y-intercepts for each of these graphs. Okay. So for the first one, I'm going to use the slope 1/2 to graph the next point. And the other one here, I'm going to use the slope negative 3. So let's see. For first one, it is 1/2. Second is negative 3. I'm going to go ahead and see. M is 1/2 at the point 0, 4, my y-intercept. My second one, my m is negative 3 for the point 0, 5. All right, so for the first one, here's 0, 4. My slope is 1/2, so I'm going to go up 1 and to the right 2. So 1, 1, 2. And then I'm also going to go in the opposite direction too. So again, even though my slope's positive, I can still go in a negative direction twice to keep it positive. So I'm going to go down 1 and to the left 2. I'm going to go ahead and connect those. All right, there's my first graph. Now next, I got a y-intercept at 0, 5. And my slope this time is negative 3 or negative 3 over 1. So I can either go down and to the right or up and to the left. I'm going to do both. 1, 2, 3, and up to the left 1. 1, 2, 3, and then down here. All right, so it looks like they intersect somewhere at this point right here. It looks like they intersect somewhere at this point right here. Now, I don't know for sure what point that is. So I'm going to go and we'll get better at solving system of equations algebraically. So I'm going to go ahead and type these in here. And actually find out exactly where my intersecting lines are. So for the first one, it is 1/2 x plus 4, which is what we got right here. And for my second one, negative 3x plus 5. And there we go. So I wasn't that far off. From my graphing. Let's see what this point is right here. 0.286, 4.413. All right, so that's roughly where our solution is. Okay. Now we can also find system of equations by using visual aids like charts and graphs. The basic idea is the same. We want to find where the two graphs intersect. And just like we saw in the graphing calculator example, you look for the x value that shares the same two y values for between each function. We can also use what's called a linear regression model to find the solution. So in your notes, I've attached a linear regression handout. I've attached to use for example 3, so I can show you how to compute a linear regression model in your graphing calculator. I'm not going to show it in this video. I'll probably do a separate video on how to do that. But just so you know, we'll talk a little bit about how to do a linear regression model. But let's go back to the textbook real quick. So here's an example of using a table to solve a problem. So you have you have models of different growth rates and birth lengths of different types of sharks. Here's the x and y chart for each equation. Here's the place where they intersect. Here's where they have the same y value. So the sharks will be the same length when they are this age. Okay? And once again, we can also use a linear regression model. There are some examples here on how to do it. You can also look at the handout to help you calculate that as well. Again, we'll talk about that at another time. But how do we know what type of system of equations we have? Well, zoom out here for a second. Here we go. So there are 3 types of systems of equations. The ones where the examples that we encountered are examples of linear equations that have a unique solution to it. Okay? So that's this first example right here. So that's called a consistent and independent. A consistent and independent system of equations is a group of linear equations that has one unique solution. And as we saw on a graph, that means that they intersect at a point. But let's say that they intersect at more than one point. Let's say I have 2 linear equations that represent the same line. Well, here you have what's called consistent and dependent. Now, what does that mean? So a consistent and dependent system of equations is a group of linear equations that has infinitely many solutions. Graphically, these lines are either the same or non-zero multiples of each other. So for a consistent and independent system, that's kind of like saying or using the example earlier, the lines intersect at a specific point, like we saw in the previous example. For a consistent and dependent system, that's like saying I have one line going up here and another line going all the way up here. It's the same line, but either bigger or smaller than the other one. Then we have what's called an inconsistent system. An inconsistent system of equations is a group of linear equations that has no solution. Graphically, these lines are parallel and never intersect. Because remember, the solution to a system of equations comes from the place where they intersect. If 2 lines are parallel, then they never intersect, which means they aren't going to have any solution. And we'll talk about a little bit later about, how does that look to us? How does that look to us when we're trying to solve algebraically, right? Okay, but for right now, let's look at an example of each one. So here you hear what they look like graphically for systems of linear equations. You have a consistent system that can either be independent, where there's one solution. It could be dependent, where there's infinitely many solutions. And inconsistent, where there's no solutions. Okay? So, without graphing, is the system independent, dependent, or inconsistent? Well, what you see here is they're taking this equation right here and putting it in slope-intercept form. Okay? But by putting it in slope-intercept form, what you're going to notice is that both of these lines have the same slope. If they have the same slope, that means they're parallel. Because they're parallel, they're never going to cross each other, right? Now, the only exception is that they were exact same line, but here it's not. Because notice that here the y-intercept is positive 3 over 2. Here the y-intercept is negative 3 over 2. If this were a plus right here, for some reason, if that were a plus, then it would be a consistent and dependent system that would have infinitely many solutions. But that's not the case here. Here, I got two different y-intercepts and the same slope. That tells me these lines are parallel. The system is inconsistent. We say there's no solution. We would say that there's no solution to this. Okay? Looking at letter C. Let's look at letter C for a minute. I'll zoom in a little bit here. Letter C, y equals 2x minus 3. Well, this is already in slope-intercept form. I'm going to put the other equation in slope-intercept form just to see what happens. Okay? So I'm going to subtract 6x on both sides. Okay? When I do that, I get negative 3y equals negative 6x plus 9. I'm going to divide both sides by negative 3. That gives me y equals, so negative 6 over negative 3 is positive 2. 9 over negative 3 is minus 3. I actually end up with the same line. I end up with the same line because slopes are the same and the y-intercepts are the same. So here, it'd be consistent and dependent. It would have infinitely many solutions. And when we answer questions like these, I want to hear both answers. How many solutions does it have? Or what solutions are there? There are infinitely many solutions. What kind of system is it? It's a consistent and dependent system. Consistent and dependent system. Okay. Now, graphing is not the only way that we can solve a system of equations. One second here. Go to the next section of the book. So, finding the solution graphically is not the only way to solve. We can also solve it algebraically using one of two things, one of two methods. Substitution and elimination. Now, substitution's it's pretty straightforward. You're taking, you're just substituting a variable in one of the equations with a value or expression used in one of the other equations. All right. Elimination involves a lot more algebra than that. But let's start with using substitution here. All right. Let's see. A second here while I reopen this. Let's try again. There we go. Yeah, here we go. All right, so let's look at this example right here, solving by substitution. What is the solution for that system? Well, as you can see, what they did here was, notice how in this system of equations, one of the variables has a coefficient of 1. If any of your variables have a coefficient of 1, then substitution is a really good way to solve the system of equations. Because what they did here in step 1, they took this equation right here and put it in slope-intercept form and solved for y. Now this value right here, what they're going to do is they're going to take that value and substitute it into the y in the other equation. Once that happens, now you have an equation in just one variable that's much easier to solve. And here they found the value of x. And once you know what that x is, go back to what your value of y was, substitute this for the x, and then you'll be able to find your y. Okay? Let's look at this example right here. let's try to find the solution to this system right here. X plus 3y equals 5, and then negative 2x plus minus 4y equals negative 5. All right, let's move this up here. Come on. There we go. All right, so here, this x right here has a coefficient of 1. So if I take this, move it over to the other side, then I'll have a value for x that I can substitute here. So let's try that. All right, so if I subtract 3y on both sides, I get x equals negative 3y plus 5. I'm going to take that negative 3y plus 5 and substitute it here. So that way, this whole entire equation is in terms of y. And if I solve for y, I'll come back here and use that to solve for x. So let's give that a try. Negative 2 times, I'll put in this for x, negative 3y plus 5 minus 4y equals negative 5. And then let's get with solving. So we're going to distribute the negative 2. So that's positive 6y minus 10 minus 4y equals negative 5. Let's combine like terms here. 2y minus 10 equals negative 5. I'm going to add 10 to both sides. So 2y equals negative 5 plus 10 is 5. Divide both sides by 2. And my value for y is 5 over 2. Okay? Now, later on we'll work some practice into keeping this as a fraction, but to stay consistent with the textbook, we're going to put that in decimal form. Now, if you're working this on Math Excel, you want to pay attention to how it's telling you to answer the problem. If it tells you to write an integer or a fraction in simplest form, this is what you want. But if it tells you to round to a certain number of decimal places, then it's okay to use a decimal. Okay? So now I'm going to take that value of y, plug it back into here. Okay? I'm going to do that over here. So x equals negative 3 times 2.5 plus 5. Okay? So I believe that's negative 7.5 plus 5, and that's negative 2.5 here. So the way that you should be answering this on Math Excel is in an ordered pair, x comma y. That's at least how I would want you to solve it if you're doing this on a test. Okay, x value is here, negative 2.5. My y value, positive 2.5. And again, once you have your solution, definitely feel free to plug your solution back into each of these to make sure that it lines up. If I plug this in here and I get 5, then we're A-okay. But if I plug this in here into here and get negative 5, I'm okay. But if at any point I plug my solution into one of these and it doesn't end up with what's on the other side, I got to go back and check my work. Okay? So this would be in decimal form. In fraction form, it would be negative 5 over 2, comma, positive 5 over 2. Okay? And that's how you would work substitution. Okay? Then we get to elimination. And elimination is a little bit trickier because it involves a little bit more math here. So there are 3 ways that we can affect the system of equations while we're doing elimination. Because when we use elimination, what we're actually trying to do is we're trying to eliminate a variable. We eliminate a variable by canceling the variable out using inverse operations, like adding and subtracting the same coefficient in front of that variable. So in order to do that, there are 3 different ways we can affect the system of equations. We can change the order of equations, right? If I'm working with 2 equations, I can always flip them around, okay? I can multiply any row or any equation by a non-zero real number. So I can multiply an equation by 5. I can multiply an equation by 1/2. I can multiply an equation by 7. And then the last one is adding a non-zero multiple of one row to another. So let's say I have 2y in one row and I have negative 6y in the other row, well, if I multiply the 2y by, and that whole row by negative 3 or positive 3, I get a positive 6y and then a negative 6y that cancel each other out. Okay, you'll see it work out when we do an example. You'll get a better idea of how to work it. Like for example here. So see, notice how in this example I have a 4x and a negative 4x. If I add those equations together, those cancel each other out, and I'm left with one variable. And then if I have one variable, then I can solve for that variable, use that into one of the other equations to find the other value. Okay? So here's an example. So like for this example right here. Notice here I have a plus 8y and a minus 8y. If I add those together, those will cancel out. Those variables will eliminate each other. And then I just add everything else. Negative 2 plus 5, and then negative 8 plus 20, that's 12. Divide by 3 on both sides. X is 4. Now I can use that variable, plug it in here, and then solve for y. I'm gonna use the top one right here. So negative 2 times 4 plus 8y equals negative 8. So that's negative 8 plus 8y equals negative 8. Add 8 to both sides. 8y equals 0. Divide by 8 on both sides. Y is 0. There's my solution. 4, 0. By the way, all of these systems that we've been solving have all had one solution. That tells me that every single system we've been working on is consistent and independent. And then there's your solution right there. Here's your solution. Here's what type of system it is because of that solution. Okay? Let's take a look at another example here. So here is another example. 2x plus 7y equals 4. 3x plus 5y equals negative 5. I want to eliminate a variable here. Does it matter which variable you eliminate? No, it does not. You just have to make sure your algebra is correct. Here's what I'm going to do. I'm going to try to eliminate the x here. I'm going to try to eliminate the x here. Again, this is 2x plus 7y and 3x plus 5y. So I'm looking for a common multiple. And when I'm looking for that common multiple, I got to make one of those negative and one of those positive. So when I look at 2 and 3, a common multiple of 2 and 3 is 6. So here's what I'm going to do. I'm going to take this equation and multiply it by 3. I'm going to take this equation, multiply it by negative 2. The reason I'm doing negative 2 is so that this, whatever I get out of here, is going to eliminate with whatever's right here. Now, can I make this negative and this positive? Absolutely, 100%. Does not matter, but again, make sure your algebra is right, okay? So, again, make sure you distribute to every part, especially across the equal sign 2. Make sure you distribute. So, on this side, I have 6x plus 21y equals 12. And then the bottom, I have negative 6x minus 10y equals positive 10. And I'm going to go ahead and add those together. When I add those together, the x's eliminate each other. And then I can solve for y. Let's see, 21y minus 10y, that's 11y. 12 plus 10 is 22. Divide by 11. Y equals 2. And now from there, it's just a simple matter of which equation do I plug back in. Let's try the bottom one. I'm going to use the original bottom equation right here. 3x plus 5y equals negative 5. I'm going to take my 2 for y. I'm going to substitute it in here. 3x plus 5 times 2 equals negative 5. So that's 3x plus 10 equals negative 5. I'm going to subtract 10 on both sides. Move everything up here. So 3x equals negative 15. Divide by 3. X is negative 5. So there's my solution. There's my solution. Negative 5, comma, 2. And I can use a graph to double check that work to make sure that it's right. I can take negative 5 and 2, plug it into my original equations, and see if that works. Okay? And if you have time permitting, if you do that, it should come out evenly. It should come out evenly. Okay? And that's how, and again, you can see right here exactly what they just did. Exactly what we just did. Now, what happens if we're solving systems of equations and we end up with stuff like this? Okay? Well, how do we know algebraically whether a system has infinitely many solutions or no solutions whatsoever? Well, let's look at these two examples. So here what I have is, I have negative 3x plus y equals negative 5. I have 3x minus 5 equals positive 5. If I try to use elimination and I added them together, what you're going to see is, when I add them together, these cancel out, and these cancel out. And I'm left with 0 equals 0. Well, we know that 0 equals 0 is always true. That tells me that I'm looking at the same line here. Also, think of it this way. If I take this line, if I take this line right here, there we go, and I multiply it by negative 1, distribute, I end up with this line right here. So it turns out these rows are multiples of each other. This is a multiple of this one, just as this is a multiple of this row. So anytime that you look at two equations and you notice that one equation is a multiple of another, that should be an indicator in your head saying, hey, that might be a system that's consistent and dependent. Okay? And that might have infinitely many solutions. When I look over here at this example, so when I use elimination, as it turns out, these two variables get eliminated, but this does not. And I end up with 0 equals 16. Well, 0 is never equal to 16. That's a contradiction. That tells me that there's no solution like this that's going to make sense. That tells me that it's inconsistent. It has no solutions. Okay? Also, if I try to put this in slope-intercept form, let's try to do that right now. Let's try to put this in slope-intercept form. So this is negative 6y equals negative 4x plus 6, divide by 6, or negative 6y equals, let's see, 2/3 x minus 1. Here, do the same thing. Let's see, positive 6y equals positive 4x plus 10. Because I got to move the negative 4x over, becomes positive. Divide, I get 2/3 x plus 5/3. So as you can see, it's the same slope, but different y-intercepts. That tells me that these are parallel lines, and they're never going to intersect. Okay? So if you're trying to solve algebraically and you get something like this, where you have something that's always true, especially like 0 over 0, then it has infinitely many solutions. Infinitely many solutions. This system is consistent and dependent. Here, if I get something that's never true, then I have no solution. And this is an inconsistent system. All right, so let's be careful in how we solve this. Make sure our algebra is correct. And make sure we're looking out for, especially for these forms of systems of equations, to see if they're inconsistent or consistent and dependent instead of consistent and independent.